Hi, David Vizard here, and you guys are watching PowerTec 10. In this edition of PowerTec 10, we're going to look at the principal deficiencies seen in virtually every aftermarket, and if it comes to that factory, 4-barrel intake. And here's what I'm basing it on. They could cast it right, or make an effort to cast it right, or they can just keep on making the same mistakes. Now, again, that sounds like another bold DV statement, but I'm going to show you in this video just how wrong and how much is left on the table on your typical 4-barrel intake manifold. But having said that, I've got some manifolds that I want to sell, and I have some manifolds I need. So let's start with the ones I need. If any of you have, and they have to be in decent shape, not brilliant, but decent and totally usable, small block Chevy Performer RPM air gap, I'm looking for 2. I'm also looking for 2 Edelbrock Victors, the ordinary Victor, not the Super Victor. So if you've got some, call me on my sales number, which is 704-675-4447. Now, what have I got for sale? Let me just grab it from over here. Now, the manifold I've got for sale is this dude here. It's off a factory 572 big block Chevy, and so there, and it's for a 10.2 Decite. It's untouched, but these are pretty nice manifold. And I'm looking for $175 for this, so that's a bargain. The only time it's spent is on the dyno whilst testing the 572. So it has seen about 4 hours of time on the engine. Anyway, okay, let's get down to business. The business is modifying single plane 4-barrel intake manifolds. Now, the original manifold here was the funnel wet manifold. This is a product of Terry Parker, who hails from Australia. I've met Terry several times when I've been out there, but the point here is that Terry and my very good friend, the late Roger Helgeson, conspired to help out in the design. Now, the thing is Terry had some to bring some compromises his end due to the fact that he's a one-man deal and not really in business other than to make this manifold, or was in business to make this manifold. There were several things that he could not accommodate on it because of deadlines on things. So since Roger and I had to phone at odd times at night to get hold of him, or he the other way around, things didn't get done as easily as they could. However, in its stock form, the funnel web manifold produces more top-end horsepower than any other manifold on a 5.0 or a short deck small block Ford. And let me show you what I've done. It's pretty clear. All the clutter off here is gone, and I put some filler here, right? It's all been cleaned up. But the main thing is, now this is the first step toward getting a 4-barrel manifold to work, and mostly because of design flaws to start with. Let me tell you about first the lengths of the runners. You can easily see that this runner is much longer than this one, or these two. Same with the small block Chevy. Now, the common fault that is made is that these runners come into the Plenum with the same size as these pair of end ones, either end here. Now, here's the problem. The more you taper these runners here, the shorter they seem. In other words, by opening up these runners to the same amount as these runners look not just shorter by the amount we see here, but even shorter yet, because tapering the runner, the more it's tapered, the shorter it seems to be to the pressure wave, and the more the pressure wave that's generated in here is, how shall I say, softened. That's not probably the right technical word for it, but I'm sure you'll understand what I mean. So the first thing is, do not make the runners across here the same size as the runners here. This is a fault that's done with every big block Chevrolet 4-barrel performance manifold that's currently manufactured, and it doesn't work. The torque will go up and the horsepower will go up if the center runners are closed down. Now, this manifold had the same problem. It is intrinsically a high manifold, really works well in the 7,000 to 9,000 RPM range. Now, I don't know if you can see it, but what I've done is reduce the size of the runners here by, that down there. Let me see if I can tip it over. What I'm indicating here is about a ½ an inch. This here is probably in the region of almost a ½ an inch of filler. So that's the thing. We need to keep the port energy up. What this does here, making this smaller, what this does here is it has virtually no effect on the flow because they were too big here to start with. However, the velocity goes up, consequently so does the port energy, and the runner looks about somewhere in the region of about a ½ an inch longer. Now that doesn't compensate for this here, but it's a step in the right direction. Making these smaller and increasing the length is good for torque everywhere, from the bottom of the RPM range where it comes on the cam right up to the top end. Right, I was going out the picture then. Now, that's not all that we're going to do here, right? The other thing is that, now, this is a Ford manifold, but I'm going to use I'm going to use a Chevrolet manifold, or a drawing of it, to illustrate the point that I'm making here. So let's swap over to a diagram of the firing order on a Chevy manifold. Here we go. Now what we're going to consider here is the taper on the runners and how that affects sizing and how that affects some adverse effects of pressure waves generated in the between the runner and the plenum. Now let me make a point here. The biggest pressure drop on the intake valve doesn't happen when the piston is going down the bore at the fastest point. Very often this is referred to as the maximum demand point. Well, it may appear to be that so, and in certain, depending on how we look at it, it can be the maximum demand point in terms of airflow. But in terms of the pressure difference between the cylinder and the port, it is far from the biggest pressure drop. The biggest pressure drop on a typical race engine normally occurs during the overlap period. So we've got to take care of that, because what happens is we get robbing of one cylinder by another in a certain area in the intake manifold, and that's what we're going to look to now. However, I do want to make one point here. Before we look at that, let's consider runner length. There's nothing you can do to get the inside runners as long as the outside ones, or vice versa. But how important is it to do so? Not as important as you may think. Now let's take a high performance street motor or a typical circle track car. They will use an RPM bandwidth that is greater than you would get from the tuning of a cylinder from a certain length. So if you have all the same lengths of runners, it's only going to operate over about 400 to 600 RPM range. Most circle track motors use more than that, right, by a long shot. So it actually works out better if you take care of the pressure waves and let them be maximized on two different length runners. Then you'll get two power spikes in there, and they'll be worthwhile because you will now shape the runners to get the best pressure wave return. So let's go and look at a drawing and see what we've got to do to get that. Let's start our investigation here at the manifold to carburetor base plate face. First, most intake manifolds are not tall enough in respect to the fact that if the base of the carburetor is too close to the bottom of the manifold, the air comes in and stacks up and cuts airflow. Now, we're looking for a spacer like this, what we call a super sucker, right? Now this could be square here or match up with the manifold like that, but basically it goes from two round holes to a exit form like this. Now the reason that these work well is that they slow down the air coming out of the carburetor and allow it to mix with the air further on down easier, and it doesn't necessarily impinge the bottom of the manifold. How much difference does this make? Well, if we put a carburetor on upside down and blow through it, technically it should flow the same as when we put it on the right way and suck through it. However, that's not the case. When you blow through a carburetor, you're blowing into an infinitely large plenum. When you suck through a carburetor, even on the flow bench it comes out and it's going to hit that plate underneath, right? But if you put it on a manifold, it's going to have a finite plenum. So what do we do about this? Simple. we use a spacer like this. Oh, I was going to say, how much does it increase flow? Well, if you blow through the carburetor and then put one of these on here so that the streamlined effect comes in, it flows well over 100 CFM more, and that's not an inconsequential amount. It'll also flow more on your manifold. It improves the quality of the carburetor. I prefer a 2-inch one. This happens to be for a specific job where there's a hood clearance issue. Now, let's go on to the next part, which is comparing the original form with the new form that we want. So let's go there. Here the arrows are indicating the original runner form. Now, point here. That original runner form is going to be very good on the flow bench because of the gradual turn into the runners. But there's a problem. Remember that pressure waves tend to get reflected from a change in cross-sectional area. Well, that big curve there represents an infinite number of changes of cross-sectional area. And it's a big curve. So here's the deal. What that curve does is damp the pressure wave quite considerably. We don't want that. It might spread it out over a bigger RPM range, but that is a ridiculously big curve. You'd do better off with a small one. Now, in terms of airflow, we've got to consider if we make too small a turn, the pressure wave tuning may work well, but doesn't flow very well. Generally speaking, we're looking for a radius of about 1/4 to 3/8 of an inch on the end of the runner. That's a pretty good rule for the bottom curve of the runner. But the top one, which I'm going to indicate again now, is a different matter. This curve has to be developed on the flow bench. The wall of this, where the spacer aligns, the wall of the manifold where the spacer aligns, needs to be formed as it turns into that runner in such a way that it does not impede flow. So the bottom line here is you start off with a small radius and you gradually increase the size of the radius until it virtually does not show up on the flow bench. Now let's look at the taper. 2 to 4 degrees. That taper is such that it maintains good flow, consistent with also maintaining a good amplitude for the pressure wave getting back to the valve. So that's the amount to use. Now I tend to go straight to about a 4-degree taper here rather than mess about with lots of others, because that seems to be about a good spot. And I've learned that from IR systems, that about a 4-degree taper down to the smallest cross-sectional area of the port, about 2 inches before the valve, is what works best. So I've applied that to intake manifold. Now remember, a typical single 4-barrel intake manifold is a runner with a finite plenum on the end, i.e. the plenum we're stuck with, whereas an IR system is a runner with an infinite plenum on the end. Should they operate differently? Well, they do, but we can transfer some rules from one to the other, right? And this 2 to 4 degrees is one of them. I'm going to use this 18-degree small block Chevy intake manifold. This was popularly the thing to use early 2000s, and it functions pretty good. Now, some of the good points about it are that it has this long radius into the turn here. However, many manifolds come out and then in and across like that. That's not the way to do it. In fact, this is not the most ideal, but it's very good. What we want is an intake which does all the turning here. So we want to start the port, this port, about here, and have it come at, this is where it's largest, and it will do the turn here. The port at the turn will become taller and narrower so that the inside wall has the biggest turn, and then it goes on into there. Now what we really want to do is, in spite of this being a big turn, the gases will predominate on this side of the runner and on the opposite side here. So what we need to do is we need to overshoot the port slightly. Now I say that there's a caveat to that. What we want to do is to favor the side of the intake port on the cylinder head that enhances swirl. Now, if the valve is on the outside of the cylinder, then favoring this side is good because the swirl will go in and round like that. But with some engines, the intake port is on the inside. So in this case, we want to overshoot this quite a bit so that the flow tends to go across like that, so that it swirls this way. So note that it's only a small point, but you know, if you're racing and pick up 5 horsepower, that's positive. If you left it on the table, that's your fault. Now, inside runners, we've dealt with that. On the Fords, they go straight in, but on the Chevys, they don't. So we still need to overshoot as necessary here. Taller intake port, taller here in the turn. That would be it for now on the runners. Now let's look at what we do in the Plenum. Now let's start the ball rolling here with a diagram of the firing order on a small block Chevy, or for that matter a big block Chevy. As we go round the firing order, you will notice that 5 and 7 draw concurrently. That is, their induction phases overlap. You'll see that cylinder 5 draws first. Now what happens here is, because the depression in the cylinder is largest during the overlap period, that cylinder 7 robs cylinder 5. So what we have to do here is to make cylinder 5 is to give it some protection against being robbed by cylinder 7. The first thing we do on this is to shape the edge of the divider such that it discourages flow on that side of the 7 and encourages flow on the side of the 5, so that it discourages flow on the wall adjoining 7 and encourages it on that same wall into 5. Also, because we are making cylinder 5, that is the inside one, smaller to conform to the stuff we've done earlier on the intake port. Now that was a Ford intake port I showed, but the same technique can apply on this number 5 cylinder. Now of course, if you swap the firing order, you have a 4-7 swap, then this happens at the other end of the manifold. So what we do here is the smaller port has higher velocity, and in such, when the pressure wave from cylinder 7 hits, and that's when the piston's halfway down the bore on 5, then it has a less ability to slow the flow down. It will slow it down, but it won't do it as much. So that's what we've got going for us there. Now, I'm sure a lot of you have seen manifolds with what we call elephant ears in. That is, the runner extends into the port, the runner extends into the plenum such that there is a protrusion that you can see. Dark manifolds do this when you look down on it. Now, they've usually got them on all cylinders in the position between the two, so you have 4 elephant ears. But here's the thing, those elephant ears actually only do anything when they're on the 5/7 cylinder, or the equivalent one on a Ford. So if you're going to put an elephant ear in, it's only really necessary on the junction of cylinder 5 and 7. Now, I'm not too sure which end is which on this. Old age creeping in again, but let's assume that this is the front of the engine and this is the rear, right? So we're going to have cylinder 5, that's this one here, draw 90 degrees before this one here. So what happens is that the pressure pulse comes up the cylinder, and that from the overlap changes sign in here, goes back as +1, right? And that persists until just past top dead center. When the piston on this cylinder is 90 degrees down the bore, or thereabouts, the intake valve opens in number 7, and the exhaust pulse sucking the gases out comes through the intake port in the overlap period and causes a big depression just here. Now this one's pulling full steam, but from a lower depression than this one. So what happens is air that was going down there tries to go down here. So what we do, now let me just tip this so that you can see better. So what we do is we cut the 5, let me see if we can see that. We cut the 5 cylinder here, we put a big radius on it that ends up in a sharp edge on the 7 side of that divider. So we've improved the ability to flow into the 5, but we've cut it on the 7, and that is a big help. Now, if we want to put an elephant ear on, we need to make it come up here like this here, right? Because most of the highest strength of the pulse is in the top half of this runner here. Now, what would work well on this is a straight one coming straight up and then in like this, and it's streamlined into that there, but not so much here. That does the trick. Let's talk about these dividers here. They need to be, except for this one here, they need to be nicely rounded, because cylinders, adjacent cylinders like this, do not draw at the same time. They draw quite independently, so they need something that looks like a ram stack entry on the runner. So this one will be sharpened on this side with a radius on this side, whereas all the other ones will be rounded. That's it. If you get that far, fine. Now let's talk about the bottom of the manifold. Many people will drill, let me just tip this up, many people will drill holes here, not going all the way through of course, but they will drill holes. Well, I've tested that and it never doesn't work. Sometimes it does nothing, other times I've seen as much as oh, I don't know, 12, 13 horsepower, right? But that's not the final way of doing it. Now, what I'm going to do is in another issue, I'm going to show you something. But before that, let's talk about another sale item I've got. Here is the cam I have, which is excess to requirements. A Howard's flat tappet cam for a 351 Windsor. Now, quick rundown on the history of how I've got this cam. My late partner, Marvin, had a friend who wanted his engine dynoed, and that was after he built it. And he asked Marvin for a cam spec, and Marvin quickly ran through our cam program for 351 Ford Windsor and came up with a cam that fitted his requirements, and it did. It gave the right idle at the right power band. It gave very good torque. Now, I've got to say, Howard's is a company which gets overlooked a little too much in the how should I say, aftermarket buzz. Their flat tappet cams have got a lifetime warranty on them so long as you follow their instructions, right? They're not made of the same, the blanks aren't the same material as most other blanks out there. They are much tougher. I've never had a failure of one of Howard's flat tappet cams. I've used maybe, I don't know, between half a dozen and 10, I suppose. Now, the engine made very good torque. It was a 10.5 to 1 motor with it had aluminum heads. No, I can't remember what they were. Anyway, I called up Robert Lew, and this is as I remember it, because this happened right before I had to go to hospital for some pretty major operation. And it was kind of an emergency operation. Now, I ordered a cam, a custom cam from Robert, going through their cam profile. Now let me give you the spec of the cam that we dyno tested. That was, let me see what the part number is. It was a 210961-08. That means the 08 means it's on 108 lobe center line. It was meant for street strip, more back toward the street. Had a power band. Well, it says here 2.6 to 6.3. Our motor peaked, as I remember, at about 6,000. Had a very nice idle. It didn't lope like they claimed it would do. And this cam was 501 thousandths lift at the valve. That's the theoretical one. It was 285 at 6 thousandths lash, and 231 at 50 thousandths. Now it worked so well, especially torque, right off, well, pretty much right off the idle speed. Used a virtually stock converter, and it ran extremely well. The engine made very good horsepower. And what happened is that Marvin, my late partner, decided that he was going to use a cam like this in a build he was doing. So I talked to Howard's, called up Robert Lew. I talked to Howard's, and we came up with an upgrade. This cam is 283 at lash, but it's 236 at 50 thousandths. So it's 2 degrees shorter at lash, but it is 5 degrees longer at 50 thousandths. It's on a 108 lobe center line angle, and the lift is 583. So basically it was a scaled up version of this other cam. Well, here's the deal. we got the cam down here, and the build never got done because I ended up in hospital for quite a while, and the pressure to do the build just faded. So it's been on my shelf for years. Can't remember how long, maybe 5, 6, maybe 7 years. Anyway, it's brand new in the box. Here it is. Now, the price for the cam, the original spec from Summit, is $212.99, or $213. And if you don't get this one, that cam's a good cam to use in a 351, right? This, for this one, I would like to get $135. Remember, it's a custom grind, and I'll tell you now, in a 350 or a 393, that's its range of use. A 350 or a 393 with some good heads on it, it will make power. Much more than a roller cam picked ad lib out of a catalog. So here we go. If you're building a 351 Windsor, I am just in the process of starting some experimental heads. Now, they're not experimental in terms of power, they're experimental in terms of the way we're doing it. If I get these heads done in the near future, they will be up for sale because I don't have a Windsor 351 Windsor to put them on. But here's the deal. They will have beehive springs on them of their E7 TE castings, right? That's the most used casting on a Mustang, 5.0 Mustang. The purpose of me doing these heads is to show a quick way for machine shops to do the heavy duty work in the port bowl, which is where 90% of the work is. So they won't be 100% ported. They'll be a super bowl porting job. They'll have new valve springs, there'll be bigger valves, and they'll be set for a compression ratio around about the 9.5 to 10.5 to 1. Now, I want some offers for these cylinder heads, right? Don't forget, we need money for doing our special projects. Don't insult me with an offer that's not up to scratch. New valves, new guides, new springs, and whatever else it needs to make them a good performance asset. So if you want the cam, the number is 704-675-4447, and no tech calls, only purchasing calls and business calls on that number. Thank you. Well, if you thought we were done with the intake manifold modifications, you're wrong. What we're going to look at now is modifications to the plenum floor. Now, I have a situation here, in as much as I've got a whole story to do on an innovative manifold that incorporated a lot of what we've talked about, plus a rather extensive modification of the manifold floor, which justifies an article all on its own, and the dyno tests. Anyway, other than that, what we'll do is we'll just cover some basic modifications to the manifold floor. First, and I mentioned this earlier on, putting the dimples in at the bottom. These need to be, the best way to do these is to just drill holes in the bottom to the point where the parallel part of the drill has gone into the material, so that it's not this shape, but it's this shape. That means that it traps the fuel in there, and it has to work hard to pull it out, and it can only come out in a relatively vaporized form. Now, the other modification, and I think Andy mentioned this one last year, that we quickly did on an intake manifold, and I guess I should have taken some pictures of it, is if you have a manifold which is relatively flat, not coming down like this, then going across the floor of the intake manifold, you make a hump, right? Usually about a half an inch, maybe 3/4 of an inch high, and you shape it so that the sides of the hump blend into the floor of the runners all around. So what this does is it allows any individual runner to be able to draw air from the carburetor, and it goes down over the hump and in easily, or any air that's this side of the plenum can flow easily over that hump. And what this does is allow the engine to make much more low-end torque. In fact, it makes a single plane manifold jump half the step between a regular single plane and a two-plane manifold. So that's what I've got to say on that. Now that brings us to the end of our treatise on a single plane, single 4-barrel manifold. It's not everything that you can do to them, but it's all I can think of at the moment, and it will give you a lot to think about in the future. Have we finished with manifolds? No. I'm going to do a manifold, show you a manifold that Mike Jones and I did between us. Mike did, there's camshaft modifications which go with this. So until then, I wish you a very good 2025. Plus, don't forget, like, subscribe, share, and get notified, etc. And a super thanks would be very good. Thank you very much for watching.